So as we ended in the last one, we're looking now at these reactions, trying to come up with a category or way to categorize the reagents so that we understand their stereochemistry and their potential mechanisms. So in this particular video, what we're going to do is look at those three-member intermediate transition states. So don't stress so much on the specifics of whether it's a transition or an intermediate. Focus more on the fact that we're going through some kind of three-member system. So again, what we're talking about is a Lewis acid or electrophile that is connected to a leaving group. That leaving group is stable on its own. So that's a big thing that I should probably actually formally add to these slides, because while we do need the Lewis acid as a nucleophile, the big differentiator here is that the leaving group is stable. Okay, so stable leaving groups, large, they're electronegative. Okay, you can go through and use different systems and say weak bases. That's fine too. Okay, if it's a weak base, it's large and it's electronegative. So pick your poison. So what we want to do is look at a couple cases on what's happening within these and think about what those Lewis acid, leaving group, and nucleophile pieces are and see how far it necessarily takes us. Right? So let's take a look. So if we were to run our reaction, and I'm already irritated that I'm cycling between electrophile and Lewis acid, but we're going to do it anyway. So if we go through and look at this, we're starting with our alkene. Okay, so here's our starting point. And the thing I really want to call your attention to is the fact that we're showing the p orbitals. So this would go back to molecular orbital theory and hybridization and all that fun stuff, because those orbitals are going to dictate how this reaction works. Okay? And in particular, it is the electrons in those orbitals that are going to react. If our alkene is asymmetric, our electrons would prefer, if you will, to be on one of those positions rather than the other. Because it's a nonpolar bond, that preference is relatively minimal, and really what's driving it is the stability of the products that come afterwards. Okay, so, but for the sake of argument, if we went through and put in our electrons, okay, and we want to work towards the right, well, those electrons are going to come out and react with our Lewis acid or our electrophile. This is going to cause the leaving group to leave. Okay? What makes this particular reaction kind of unique is that if we looked at this in the context of what we saw for our acid bases, we would have our electrophile here, and we would end up with this intermediate, okay, with the positive charge on that carbon. It's not that we don't have lots of evidence for that, or we don't have evidence for that. We do have evidence that that is forming to a certain extent. But what we notice, okay, very heavily is that that positive charge doesn't act like a normal carbocation would. And what I mean by that is a normal carbocation has lobes because of the p orbital, which would mean if we looked at the nucleophile could potentially drop electrons into either spot, and that's not the case. Okay? Interestingly, what we see is that the nucleophile only drops electrons into the opposite face from the electrophile. Okay? Well, what that would suggest is that the electrophile is somehow blocking the other lobe, okay, the other place for the nucleophile to attack. So the best way to describe that would be to say that there's a bond between the electrophile and that carbocation. Okay, well, that bond would then need to be represented back in our mechanism. Hence, we're looking at the lone pair electrons immediately reacting. This is where I said the electrophile, which accepts electrons, is also acting as a nucleophile. Right, because it has that pair of electrons. Right? Why did we not see this in the case of the acid-base reaction? Well, we could have if hydrogen would have been able to have 4 electrons around it, and it can't, right? Because we need 1 from the bond to our halide, and then we would also need a lone pair on the hydrogen, and we don't get that with hydrogen. This is why our electrophiles become a little bit dicier and we have to pay a little more attention to them. So the overall result is that when we're looking at the mechanism, this becomes the arrow pushing. Our pi bond comes out, reacts with the electrophile, it ejects the leaving group, and simultaneously, a lone pair on the electrophile reacts back with the other carbon of the alkene. Okay? That's what results in what we see here, which is a 1, 2, 3 membered ring. Okay? Hence the terminology I was using. These are 3-membered intermediates. Okay? So once we're at this point, now we would have to decide, do we move forward or not? Okay? One thing that I've left off here would be the charge associated with the electrophile. Okay? In this process, it is possible that the electrophile neither gained nor lost electrons and is therefore neutral. If it is neutral, that does not look like the word neutral, so let's try that again. If it is neutral, the reaction stops. Okay? There is no nucleophile, it just stops and we get a 3-membered ring. If it is charged, then the reaction continues. And to continue, we would need to find a nucleophile. So we'd look in our solution for that nucleophile. That nucleophile in our second step is going to have to backside attack that ring structure. It can't come in from the same side because the electrophile is blocking that position. Okay? So when we look at the end result, we will see the electrophile, and of course I drew arrows to the different spots. Okay? Breaking the electrophile off. We see the electrophile on one side of our pi system, of our old pi system, and we see the nucleophile on the other. So the result here is that we would get a trans alignment of those two pieces. Okay? This would be known as anti-addition because they're added on opposite sides. Okay? The next part that's kind of tricky here is this really only covered half of my drawing. It didn't address the other half. Well, what's going on the other half? Well, if we go through and look at that, isn't it the same thing? Okay, there's our mechanistic step. Okay, our first one to form our electrophile, our 3-membered ring. Our nucleophile comes in, attacks, breaks the pi bond open, and we would end again with the trans alignment of those products. So why are we showing two different results? Okay, well, the two different results is that the pi bond has electrons that could exist on either half of that system. If they're on one half, they'll result in the electrophile nucleophile arrangement that we've got on the left. If they're on the other half, they'll result in the electrophile nucleophile alignment on the right. Well, does that matter? Yes and no. That's all really going to depend on the starting symmetry of the molecule. If that starting symmetry was perfectly symmetric, well then it doesn't really matter. And now the relationship between those structures could very well be enantiomers. Okay? If it was asymmetric, well now it could really matter and we could end up getting diastereomers. So the relationship between those products is largely dependent on what the identity of the nucleophile electrophile are and the identity of our starting alkene. So how would you know what happens? Well, the way that I deal with alkenes is you always get two products, minimum, always. Okay? The relationship between those two structures could be identical, in which case officially there's only one. It could also be that they're non-superimposable mirror images, which is now technically two products. Okay? Or they're non-superimposable and not mirror images, which now means they're diastereomers. So when we think about our addition reactions, you should always, always, always be saying two products every time. Okay? The next part is deciding what is the relationship between those two structures that came out. If they're identical, then officially one product. Okay? There were still two different attacks, but it resulted in the same thing. Okay? So you got to be a little bit more careful and nuanced with that, which really means we need some practice to look at. Okay? Before we look at practice, let's look at some potential electrophile sources that could fit the bill here. And if we go through and look at this, the classic one is bromine, Br2. Okay, so the first thing that students do is they look at that structure and they go, electrons. Okay, and if it has electrons, it must be a nucleophile. Okay, so this can't fit the pattern because I need an electrophile to react. This is where we have to slow down a little bit, okay, and we have to actually evaluate what's going on. It turns out that our elemental halogens are all electrophiles. Okay, well, why? You're focusing too much on source of electrons or not. Focus instead on leaving group ability. If one of those bromines took the electrons, I would form Br minus. Is that a good leaving group? Well, yeah, that's large and it's electronegative. It's also an incredibly weak base. That's a phenomenal leaving group, right? What would it leave behind? Well, the other bromine would have lost electrons and would have therefore, become positive. There's the electrophile, right? So there's our pattern. This is electrophile leaving group, right? Additionally, what does that electrophile have? A pair of electrons that could theoretically be donated in to stabilize that forming potential carbocation. There were some air quotes associated with that, but I was drawing, okay? So Br2 is our classic electrophile. Always remember it as an electrophile. It's going to show up again and again and again. It's an electrophile, electrophile, electrophile. Okay? So what next? Okay, well, we said diazomethane fit the bill on this. Okay? Diazomethane is a really tricky one for a couple reasons. One, it's incredibly explosive. So explosive that people that regularly work with diazomethane are usually missing fingers because of their glassware exploding. And I'm not lying, at least that's what I've been told. Okay? So why is it so potentially electrophilic? Well, right off the bat, we've got a hint that that carbon is our reactive species. Okay? The rest of it is going to come from actually drawing out the Lewis structure. And if we draw out the Lewis structure for diazomethane, we would have something along these lines. Okay? And you might say, well, that's not a big deal. Okay? That doesn't allow me to see that reactivity. If we push this out a little bit further, we could then see a lone pair of electrons building on that carbon, nitrogen, triple bond, and we'd have a positive there. And we'd have a negative on our carbon. You might again say, well, I don't really see the reactivity. What if we did this? Okay, so now we're no longer looking at resonance. We're looking at a chemical reaction here because I'm breaking a sigma bond. The result would be nitrogen triple bonded to nitrogen. That should look really familiar. That is nitrogen gas. Nitrogen gas is one of the most inert gases that we can work with. And in fact, it is used typically as an inert atmosphere. Okay? And here's where you might be like, well, but dude, if you did that, that carbon would only have 3 groups of electrons. Yeah, it would. And its hybridization would be sp2 to account for those 3 groups, which would mean there's a leftover p orbital. So a good way to think about this is that we have that carbon with a lone pair of electrons and an empty p orbital. Well, why is that important? What could you put into an empty p orbital? Electrons. So our structure is an electrophile. Does carbon want that lone pair of electrons sitting on it? No. That carbon can act as a nucleophile. Okay? How reactive is this? Well, nitrogen really wants to fly off this structure. So while we're forming this incredibly reactive carbon, the nitrogen gas becomes so incredibly stable on its own that that's what drives this reaction forwards. This does mean that this carbon becomes exceptionally reactive and will grab a hold of pretty much anything actively out there or actively nucleophilic, which is how it reacts. And the result is that we would go through the same cyclotri-intermediates, right? Because we're really only having one atom attack. And that's kind of a neat system, right? What else could we do? Well, now we're getting a whole bunch of atoms coming into this. And you might be like, well, there's no way that this could potentially work. But again, we want to go through and look for our pieces. Remember I said that leaving group is our key piece. If I had these electrons come over here and here, okay, what have I done? Well, I'm breaking a sigma bond. So this would be a chemical reaction, not resonance. And what I've formed here is a leaving group with that negatively charged, it's leaving because it took the electrons, a negative charge. Well, negative charges aren't stable, except it's oxygen, which is highly electronegative, and lots of resonance. So those two pieces contribute to that being a great leaving group. Well, what about the other piece? Okay, well, the other piece would now be that oxygen with two lone pairs connected out to that hydrogen. It just lost electrons. Wouldn't this be formally positive? It's similar to our carbene in the respect that it does have a place to accept electrons, and that is incredibly reactive. Okay? So that piece would never form on its own, but if, say, we had an alkene donate electrons in, well, now we could get our connection. We could get everything to react out, and we'd form our connection, okay, to our alkene. We'd lose that pi bond. We have those electrons, could potentially react back instantly, okay, because those electrons are there. It fits the bill for our cyclotri-intermediates. Right? So again, similar system. You're looking for those leaving groups as ways to kind of build you through this. And then the last one has the exact same leaving group that we saw already. The one thing that I've added to this that you typically don't see in textbooks, that I find kind of irritating, they're hiding the chemistry of the mercury. There is a lone pair or an accessible lone pair of electrons that can react as our nucleophile. So we're getting that carboxylate as our leaving group. Okay? Once it leaves, that mercury can both accept electrons and donate them. Mercury's awesome in that respect, that you're dealing with those d orbitals, large, it can share those electrons out, and that's really what's driving it. It's one of the reasons why mercury is very, very toxic, because how it can interact in these situations. Okay, which sets us up now with, well, let's actually see what happens when we go through and react these things out. So you've seen it encountered a couple times before. I would really like you to go through and attempt these, which means you should hit the space bar, click pause, do whatever you got to do, and try and predict out your products. Okay? How much? As much as you possibly can. Okay? Once you think you've got it all nailed down, you can go ahead and unpause, and we will talk through it. And because I don't trust you, I'm going to ask a question anyway right now. I think about it. There's another slide here. There is a workup on the mercury. We're trying to ditch that mercury atom. We need something to force it off. What we use is hydride, H-. Okay? It only works when supported by boron, which is going to be confusing because we'll see a boron reagent later on. But NaBH4, okay, due to the electron configuration, the dynamics of our boron structure, it would prefer to be neutral with an empty p orbital. That empty p orbital is what's holding the hydride's electrons. So when you see NaBH4, really what we're saying is that these electrons can come in and eject. It's a lot more of a complex mechanism than that, but I kind of don't want to deal with it right now because of time. And it's not super valuable for us to spend our time looking at. Okay? So the end result with our mercury reaction, for those of you that were pushing towards that, was adding H and OH across the pi bond, and it looks like I've got that hidden under there. Okay, I know I ran through that one really fast to the end. If you need me to do that one again, feel free to let me know via email or Piazza. And with that, I'm going to say we need to be done because that was stupid long. Thanks for listening.